Okay guys, question 7, titrations and acids and bases. This is just all the theory. Okay, so according to Bronsted-Lowry, he says that an acid is a proton donor, okay, and a base is a proton acceptor. You'll see what that means just now. And then according to Arrhenius, he says that an acid is a substance that produces hydronium ions in water, and a base is a substance that produces hydroxide ions in water. Okay? And then it's just general knowledge that a strong acid ionizes completely in water, and a strong base dissociates completely in water. Every single one of these 6 points I've made so far can be asked as a straight question, like define strong acid, define strong base. What does Bronsted-Lowry say an acid is? What does Arrhenius say an acid is? Etc. Okay, then we have a little formula. And this formula basically tells us the pH of an acid or a base depending on the concentration of hydronium ions. Alright, so if we know that we have a 0.5 mole per dm cubed concentration of HCl, then we know that the concentration of hydronium ions is going to be 0.5 as well. So we just plug that into this formula right here as the concentration. Note the square brackets means concentration. And also H plus and H3O plus, same thing. It's just hydronium ions. And yeah, we just plug in 0.5 there and it'll tell us the pH of hydrochloric acid at that concentration. Okay, so then another one is hydrolysis is a reaction of a salt with water. Just remember this definition. Hydrolysis is a reaction of a salt with water. Okay, and then an acid plus a base, which is a neutralization reaction, because you're basically neutralizing the acid with the base or vice versa, and that produces a salt plus water. So for example, hydrochloric acid plus sodium hydroxide gives us sodium chloride plus water. Sodium chloride is a salt. So an acid plus a base gives us a salt plus water. Just remember how to do those equations. They can come out for some marks. Okay, and then 7.3 in November 2015, there was a question. It said, calculate the pH of 0.5 mole per dm cubed of sodium hydroxide, right? Okay, so we know that pH is equal to negative log H3O plus. Okay, but NaOH is a base which produces hydroxide in water. So we can see how NaOH dissociates. We'll have NaOH and then we add in some water and it's going to give us Na plus OH minus. So we're just breaking those apart. We know it's a strong base, so it's going to dissociate entirely into its ions, right? Yeah, so we know that the concentration of OH minus hydroxide ions is 0.5 mole per dm cubed. So we still need to find hydronium ions so we can use the formula. So we still need to find the concentration of the hydronium ions to use the formula. So we have this other little formula. It's Kw is equal to H3O plus multiplied by, well, the concentration of hydronium ions multiplied by the concentration of hydroxide ions. Okay, and then this Kw is equal to 1 times 10 to the negative 4. And when we plug in the concentration of OH minus, we'll have one unknown, and that's H3O plus, and we'll get that the concentration of H3O plus is 2 times 10 to the negative 4 mole per dm cubed. So now we can go plug in 2 pH is equal to negative log concentration of H3O plus, and we get the answer 13.7. So we know that sodium hydroxide is a base, so that seems kind of reasonable, right? So if you look at our pH scale, we know that 0 to like 3 is like very strong acids, and then from like 10 to 14 is a strong base, and 7 is neutral. So 0 is the strongest pH for an acid, and 14 is the strongest pH for a base, and then 7 is neutral. Okay, and that makes it like, it helps us like realize that, okay, 13.7 is a kind of reasonable answer because it's pretty high up on the pH scale, and NaOH is a pretty strong base, so fair enough. So then we get to acid-base pairs. So basically, we know that Bronsted-Lowry This is actually two people, I think. They both came up with this. And they said that an acid is a proton donor, right? So it donates H plus ions. And a base is a proton acceptor, so it accepts H plus ions, right? So let's look at these acid-base pairs. So we have NH3 plus H2O, right? I know H2O is just H2O, but it kind of acts as an acid in this base. So this is basically us dissolving a base in water, right? So we know that this base is going to accept protons. We know ammonium is a base, right? So it's going to accept protons. It wants to accept protons. So it's basically, if you look here, it's conjugate acid pair. It's conjugate acid. NH3 wants to accept protons, so it accepted an H, and now we end up with NH4 plus. Okay, and then if we work backwards, this acid wants to donate. So going backwards this way, we find out that, okay, look, this acid has lost a proton, and that's why it's the acid. So because going backwards, it's losing a proton. Okay, and then for this one, H2O, okay, it's an acid. We look at it, and we know that this acid wants to lose a proton. So on this side, it ends up being OH minus. So it's basically lost a proton. And this base wants to accept a proton going that way. So we can see that its conjugate acid has accepted its proton. Okay, another example, we have an acid plus a base, and we want to see how we want to just get acid-base pairs. So we have HCl as an acid, we know it wants to donate, so basically we expect it to lose the H going forward, which it has. Okay, and then we have Cl minus, when we expect it to gain a proton going this way, which it has. And NH3 base, ammonium, we know it wants to accept a proton, which it has. And then ammonia, the ion, we know it wants to lose a proton, which it has going this way. Cool. I'll get back to you guys with the calculation.